Hey there, welcome to yet another installment of Real Variables. So anyway, we're going to do the mean value theorem today, and the mean value theorem we cover in Calculus 1, and so I'll kind of just give a little bit of a refresher about what it means, and then we'll do the proving part of it. The mean value theorem is extremely important for the proofs of integral calculus. It relates the derivative to the original function, and it allows us to prove, among other things, the fundamental theorem of calculus, which is obviously important to calculus because it's called the fundamental theorem. It wouldn't be fundamental if it wasn't important. So the mean value theorem basically says that you always hit your average. So as an example, here, if you average 70 miles an hour on a trip, then the mean value theorem says that you were actually going exactly 70 miles an hour along the way. At least once. Now, obviously, that is probably unlikely. You probably hit 70 multiple times, but the mean value theorem guarantees that if you have a continuous differentiable function, that it will always take on the values of the average rate of change, over a closed interval. And so that's what the mean value theorem says. Another way to think about that is that if you have a secant line which connects two dots, 2 points on a function, then you have a tangent line in between those 2 points on your function that has the exact same slope as your secant line. All right, so in order to prove the mean value theorem, so let me state the mean value theorem first. All right, and then in order to prove it, we're actually going to prove a more basic theorem called Rolle's theorem, and then use that to prove out ourselves that other part. So the mean value theorem itself says that if f is a differentiable function, and I'm going to state it as basic as I can. The generalized mean value theorem is what we prove in here, but the basic mean value theorem says this, that if f going from A to B into R is continuous and differentiable on the open interval, so we don't have to worry about one-sided derivatives, then there exists a point in the open interval such that the derivative at that point is equal to the average rate of change over the entire interval of the function. So again, what this does is this relates the derivative to the original function, and that's really important for us to be able to talk about antiderivatives and stuff like that. And so that's where we're going to be heading. Okay? So again, the generalized mean value theorem is written on is theorem 415, and we're going to prove the general one, and then the specific mean value theorem that we use comes out of that if we just let the general mean value theorem has two functions in it, and so we just let the second function be 1, and it works out that way. Or sorry, not 1, just x. Anyway, let's get to it. To prove the mean value theorem, we want to actually state and prove a more basic theorem, and that's Rolle's theorem. Rolle's theorem has the same hypotheses as the mean value theorem, but it has an extra one as well. F going from AB into R is continuous, differentiable on the open interval, and the endpoints have the same y value. All right, so our average rate of change then is just 0, right? So that's not part of the theorem, that's just showing you what's going on here. So this is the hypothesis. If f is continuous differentiable and has the endpoints equal to each other, then what does that mean? There exists a c in the open interval such that f prime of c is equal to 0. Okay, and so here's the idea behind this, that if you have a function and that function has endpoints that are the same, right? F of b and f of a are the same. So these are directly across from one another, right? That's supposed to be a horizontal line, really nicely done, I'm sure. As you can see, it's a really nice line. Then that's horizontal, right? That's a horizontal line across there. So what happens? The only way to get from here to here would be you have to go up and come back down, or you can go down and come back up, right? But regardless of which one happens, there's a place here where you have a horizontal tangent line. And so that is where you have a local max here or a local min here. And so you've got to have the first derivative equal to 0 at that point. The only other way you can have going up and coming back down would be if you weren't continuous, you disappeared, had an asymptote, something like that. That would be violating here. And the other possibility would be if your derivative didn't exist, you could have a cusp or something, but that would also violate this. So the fact that you have to be continuous and differentiable takes away all of the other ways to get from A to B and end up at the same y value. So that's the plan anyway. That's the idea of how we're going to prove this. Okay, so let me get rid of this stuff and come back and actually just do the proof now. Okay, so the proof of this is very simple. We're going to start off here by the extreme value theorem. F is continuous on a closed interval, and so F has a max and a min on A to B. All right. Let big M equal the max of f of x, where x is going from A to B. And let little m be the value, these are y values, the minimum value of f of x as x goes from A to B. Okay, so just so they're easier to talk about, big M and little m are the y values there. Okay, and so if big M and little m were the same, then the only way that's possible is then f of x is equal to some kind of constant, k, and then what's the derivative of a constant? For all x in the AB, right? So this is kind of a special case. This is like case 1 sort of, but it's kind of a silly case almost, but you do have to take it into consideration. And so otherwise, if that's not the case, big M has to be bigger than little m because a max is more than a min, obviously, right? And so we are going to define, without loss of generality, C to be the point where the function attains its maximum, right? It's not a supremum, it's a maximum, so it actually gets there. So let C is the value, or is the first value, maybe I should say, because we're not guaranteed it's unique, in AB, the first value moving from left to right, such that f of C equals m. big M. Okay, and we could do this with little m also, but it doesn't matter which one I use, so I'm just picking big M. It doesn't really matter. All right. Therefore, for small values of h, and what I mean by small values is close to 0. Could be positive, could be negative. All right. But we do need it to be defined such that C plus H is still in A, B, right? Because C is in the open interval. C can't be the endpoint, so therefore there's a small amount of H's that we could pick on both sides here. And so we're going to do that. So since f of c equal to m is the maximum value, right, so let's come back here. Therefore, for small values of h close to 0 such that c plus h is still in there, we have that f of x, c, f of c plus h minus f of c has to be less than or equal to 0. Right? Again, it could be, they can be equal to each other. But you can't be bigger than m, right? So that's true all the time for any value of c plus h. It's always less than or equal to f of c. And so what that means is, as we take a look at the limits, right, because we're talking about the derivative. Let me go to a new page. So for f prime of c, which is equal to what? The limit as h goes to 0 of f of c plus h minus f of c all over h. That's the definition, right? We notice that if we're taking a look at the limit as h approaches 0 from the right-hand side, what can you tell me about this? Right? We know the limit has to exist by the given, by hypothesis, right? It's differentiable, so we know this exists. We notice that from the left-hand side, this is less than or equal to 0 up top, and this is greater than 0 on the bottom, right? That's coming from the right-hand side. H is bigger than 0, but we just talked about the fact that f of c plus h minus f of c is always less than or equal to 0, and so this is going to be less than or equal to 0. Whatever the limit is, it's going to be less than or equal to 0 because you have a negative divided by positive. But if you take the limit of the other side, as h approaches 0 from the left, the numerator is still, right, it's still less than or equal to 0. But the denominator now is also less than 0, and so that means you're converging to something that has to be greater than or equal to 0. The denominator can't be 0, and so this is less than or equal to 0 up top, and this is less than 0 on the bottom, and so two negatives become a positive, and so you have a limit where from the left-hand side your limit has to be less than or equal to 0, and from the right-hand side your limit has to be greater than or equal to 0. But since the limit exists, the only number that satisfies both of these is that f prime has to be 0. All right? So since the derivative has to exist and the one-sided limits are both greater than or equal to 0, less than or equal to 0, then you've got the derivative has to be actually equal to 0. Okay? So that is the basics of Rolle's theorem And again, Rolle's theorem just is a specific case for the mean value theorem, right? If your average rate of change is 0, you have to hit your average. That means the derivative has to be 0, and that's what happens. So you can read through in the text section 4.3 is where we are, and remark 4.13 and remark 4.14 talk about examples of functions who are continuous everywhere but one point, or they're differentiable everywhere but one point, and Rolle's theorem fails. And so obviously that is just giving you the indication that we're doing the best that we can with the Rolle's theorem. The hypothesis is exactly what it needs to be for Rolle's theorem. Okay, and so for the generalized mean value theorem now, and again, we usually use it in context. We usually use it with just one function, but the generalized mean value theorem is if f and g are both going from a to b, continuous and differentiable on the open interval, then there exists a c in the open interval just like before, such that, I'm going to write this a little bit differently here, such that f prime of c over g prime of c is equal to f of b minus f of a over g of b minus g of a. All right, so this actually gives us a relationship between two functions. And again, if we let, note here, if g of x is just x, then g prime of c is c. G prime of c is 1. The derivative of x is 1 all the time. So g prime of c is 1, and g of b minus g of a is just b minus a. And so this guy becomes f prime of c over 1 equals f of b minus f of a over b minus a. So if g of x equals x, then this is the basic mean value theorem that I talked about in the beginning. And in your textbook, it's actually listed as a second part, but it's just letting g equal x. All right. So I've got to turn off my mail. Got to remember to do that. Okay, so the proof here, proof of the general mean value theorem, is that we create this really complex, funky looking function that we wouldn't ever think to come up with unless we knew what we were trying to prove. All right, so you let h of x, we define h of x to be f of x times g of b minus g of a minus g of x times f of b minus f of a, and it looks weird. Remember that these guys are constants, right? So since f and g are differentiable, so is h. And if you take the derivative, it's just a very basic, there's no product rules or anything like that because these guys are constants. So it's just f prime g of b minus g of a minus g prime of x, g prime f of b minus f of a. All right, so there is the derivative. Now, what's special about h, however, notice that if you plug in h of b, you get the same thing as h of a. Okay, so I'm going to let you verify that, but if you plug an a in here and then you plug a b in here, all right, the middle terms cancel, and you have, f of a, g of b or sorry, you have f of a, g of a, and f of b, g of b. And so you get both of those, and h of a and h of b are the same. So anyway, I'll let you verify the algebra there. And so so we have g of h is different. F and g are differentiable, so is h. That's true for continuity too, right? Obviously, it can't be differentiable if it's not continuous. So, but again, this is clearly continuous if f and g are, and so h satisfies Rolle's theorem. That's why we made this crazy h function. So what does that mean? There exists a C and AB such that h prime of C equals 0. So 0 equals, come back up here to the definition of the derivative, the derivative right here. So 0 is equal to f prime of C, g of b minus g of a, minus g prime of C, f of b minus f of a. So take this to the other side, divide, blah, 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 do the algebra. You can get there, okay? And the reason that the generalized mean value theorem is written in the way that it is, a ratio of two functions instead of one function derivative equal to its average rate of change, is that we're going to need that to prove L'Hopital's rule. That's how you prove L'Hopital's rule, is using the generalized mean value theorem. And so that's why that's important, okay? We've talked about increasing and decreasing functions before, and we know what an increasing function is from calculus, a decreasing function is from calculus, but the mean value theorem actually also allows us to prove the basic fundamental concepts of calculus that we utilize every day when we're looking at trying to analyze our functions. And so Theorem 417 gives us exactly that. We having fun yet? I know this is really weird, and I don't even know what to say. I can't read my audience, so I don't know when I need to wake you guys up with a stupid math joke or something. Anyway, so we're going to talk about increasing and decreasing. In our textbook, of course, they call it strictly increasing and strictly decreasing, whatever. If you want to be strict about it, dunch. So let f go from A to B into R such that f is continuous on the closed interval and differentiable in the open interval. This is our standard hypothesis for this section. Then there are three things. If f prime of x is greater than 0 on the whole interval AB, then we say f is strictly increasing. And again, in calculus class, we usually just say increasing. All right, so f prime is then f is strictly increasing on that entire interval. We do not include the endpoints. Okay, and he does include the endpoints. All right, there's some technical stuff here that we'll talk about that I don't get into in my calculus class, and that's okay. And then obviously the other direction, if f prime of x is less than 0 on the entire interval A to B, then f is strictly decreasing on the interval A to B. And again, in calculus class, we typically do not include the endpoints. There's a slight reason for that, and I'm not going to get too much into it right now. For the second part of it, if f prime of x is equal to 0 on the entire interval a to b, then f is a constant function, at least for the closed interval ab. Okay. And then one more piece here that doesn't really go with this stuff but is important for later. If g from a to b into r is also continuous, differentiable on the open interval, and the derivative of g is equal to the derivative of f for the entire interval a to b, then what do we know about f and g? F and g is they differ by a constant, and there exists a real number c and r such that g of x is just f of x plus a constant. The only way that two functions can have the same derivative function, right, same derivative everywhere, is that they are the same function basically, except they differ by a constant, a shift vertically up and down is the only difference. Okay, so we're going to prove this. Hang in there. This is the last thing we're going to do in this section. This section continues on with some starred material. We're not going to do the starred material. All right, so don't worry about anything past Theorem 418, which is just talking about one-sided derivatives and one-sided continuity and stuff. And so you can read over that. But let's go one more page here. Give me one more page for the proof. All right, so this is the proof of 417. And so for part 1, right, choose x1 and x2 in AB such that, well, actually I can choose them in the closed interval such that x1 is less than x2. Then by the mean value theorem, there exists a C in the open interval x1 to x2 such that f prime of C equals f of x2 minus f of x1 over x2 minus x1. But x2 minus x1 is always positive. So if f prime of C is positive, then f of x2 has to be bigger than f of x1, which means that it's increasing, and that's what we wanted to show. If f prime is less than 0, then again the denominator here is always positive because x2 is bigger than x1, so f of x2 would have to be less than f of x1, and that's the definition of decreasing. Okay, these are both by definition, right? And so that's all it is. It's that simple. For part 2, if f prime of C is equal to 0, then by part 1, f of x2 would have to be equal to f of x1. But that was for any choice of x1 and x2 in here. Oops, again, it's the closed interval, right? In the closed interval. And so if they're always the same, no matter what I choose them to be, so f has to be constant. Okay. And then finally, for part 3, let's go down the page here. For part 3, since f and g are both continuous and differentiable, so is the function f minus g. So f minus g prime has to be so since f minus g prime 0, so f minus g all prime is what? F prime minus g prime, but this is supposed to be 0 by the given. What happens when a derivative is equal to 0 all the time? Then by part 2, f of x minus g of x, that function, sorry, shouldn't write it that way. The function f minus g of x would have to be a constant. So that means that f of x minus g of x is equal to a constant, and we get what we need. And I think I have the signs in the wrong direction, but whatever. Okay. So that's the basics of section 4.3, mean value theorem. You definitely want to take a look at some of the problems in the text at the end. I'll shoot you an email and tell you which ones. All right, and so you'll have it in writing. So anyway, thanks for sticking with me, and I'll try to make these a little bit quicker or a little bit more dynamic or whatever. I'm still learning how to do it myself, so hopefully that was helpful. And as always, shoot me an email with questions. See ya. Bye.